And okay, so I'll actually also share. So, you know, so the last class we ended at this various ways, various properties of black body radiation, including the Planck spectrum, the defining property of a black body, that its spectrum is universal, given by the Planck function. Okay, so today we will actually talk in terms of, we'll talk about more the microscopics of radiation processes. Okay, let me start sharing. Okay. Okay. So yeah. Okay, so so I hope everyone is actually reading up, because the material can, if you don't read continuously, the material can become overwhelming very quickly. And if you read, you can also ask questions in the class. Okay, so let's get started. So we were actually talking about this concept of equilibrium, right? So there is equilibrium between the matter particles. That's when matter establishes a Maxwell-Boltzmann distribution. And then there is the concept of equilibrium between matter and radiation, and that's when your I nu approaches B nu for thermal emission processes. And then matter and radiation are in equilibrium. So let me actually define one thing before I move on. This is local thermodynamic equilibrium, LTE. So let me use a thinner pen. This is too thick. So this is local thermodynamic equilibrium, right? So when we do thermodynamics, like in our undergrad classes, we actually just talk about these big these pistons and volumes being compressed by these pistons. So we are considering, like, we are not considering any spatial structure. But if you consider, for example, the sun, right? We know that the surface temperature of the sun is 6,000 Kelvin. Right, 6,000 Kelvin, and the center of the sun can be a few million Kelvin, right? So what about, how do we sort of, the sun, the plasma in the sun, matter in the sun is in thermodynamic equilibrium, but it does not have the same temperature, right? So temperature, for example, is a function of radius. So this is called local thermodynamic equilibrium, in the sense that your particles still have Maxwell-Boltzmann distribution function, but the temperature, for example, is given by given as a function of R, rather than being a global constant, right? So if you consider a fluid volume here in the sun, it will have the local temperature given by the temperature at that radius. Okay. So this is the concept of local thermodynamic equilibrium. So you have variation of thermodynamic properties at large scales, but locally, when you consider small fluid elements and apply thermodynamics to it, they have a constant temperature. So basically, this is sort of the length over which your temperature changes, but the volume elements that you're considering are much smaller, right? So delta L is much less than capital L, where L is the scale at which the global properties change. So this is local thermodynamic equilibrium, in contrast to global equilibrium, where the whole object has the same temperature, same pressure, and so on. Okay, so this is LTE. Okay, so now we can actually move to, so this is an important term that appears and you should be aware of what it means. LTE, local thermodynamic equilibrium. Okay, so now we will actually move to these Einstein's coefficients. So you may have heard of these, but so Einstein's coefficients. So till now, we have dealt with radiation in a macroscopic sense, right? You recall we did the radiative transfer equation and we were using alpha nu, the absorption coefficient, and J nu, the emission, the emissivity or emission coefficient, right? They are macroscopic quantities, but we should be able to express these things in terms of microscopic description, and that's where Einstein's coefficients come in. So what Einstein did, so this sort of came in 1917. In fact, I've actually posted the translation of Einstein's original paper, which is actually very readable here in the files section where I have reading material. So here, class material, so useful papers. So this is Einstein's 1917 paper. It's a English translation. So you can actually check it out. It's actually quite good. You can actually understand it. It's very simple. It's very simple and clear. Okay, so I have put it there. And the other thing that I have put there in useful papers is this Physics Today article by Kleppner about Einstein's 1917 paper. So this appeared in 2017, and it was like, in 2005, right? The golden year of Einstein. So there was like an issue of various, various works celebrating Einstein's contributions, and this is by Daniel Kleppner. So here actually he talks about why this paper is so important. So what I'm going to cover in this class are some concepts from these this paper. Okay, so I encourage you to read these things because they, when you read original material, you get much more insight than when you read it in your class, in your coursework. Okay, so let me go back to where I was. My God, where did the writing go? Okay, I think I should not have gone there, but let me continue. I didn't write much, and I think it will appear. It's just a problem of syncing, because I think I was in the same I was in the same, so October 21st, part 1. So this is that. Okay, so let me continue. I will again. So Einstein. Okay, it appeared. Oops. There's like a gap, lag. Huh. Okay. Okay, so by sort of looking at the Planck function, the form of the Planck function, actually Einstein guessed some fundamental microscopic processes happening in radiation. Okay, so what are these fundamental processes? There are 3 processes. The first process is spontaneous emission. Okay, spontaneous emission. Okay, so let me actually draw a so a two-level system. So he considered a two-level system, 1 and 2, right? So the energy difference between them corresponds to, so this is the energy difference between these two electron levels, say in some matter. So this corresponds to photon energy, or energy nu naught, h nu naught. Okay, so if an electron goes from level 2 to level 1, it emits a photon of frequency nu naught. Okay, and if an electron in level 1 absorbs photon of frequency nu naught, it can transition from level 1 to level 2 after absorbing radiation. So these are the microscopic processes corresponding to emission, which is described by macroscopic J nu, and absorption, alpha nu, which is the macroscopic variable, okay, macroscopic concept that we use. So spontaneous emission, right? And the spontaneous emission is quantified by a coefficient which Einstein called A21. Okay, so let me write down what it is. It is transition probability per unit time for spontaneous emission. So basically what Einstein is saying is that if you have electrons in level 2, they have some probability of jumping to level 1, to the lower energy level, and emitting photon of frequency nu naught. And that probability is quantified by this coefficient A21, which is the probability per unit time for spontaneous emission. Okay, so the second process that he identified was absorption. Okay, and the coefficient for absorption. So basically what is needed for absorption? For absorption, we need the background photons, right? We need background photons which can be absorbed by electrons in level 1, and they can be promoted to level 2 after absorbing that energy from the photons, right? So you require presence of photons for absorption to happen. If you don't have any photons, then these electrons cannot jump to level 2. Okay, so let's say so we can actually define probability per unit time, right? And this is proportional to, right, probability of jumping from 1 to 2 is proportional to density of photons with energy h nu naught, and proportional to number density of electrons in level 1, right? If you don't have any electrons, any atoms with electrons in level 1, you will not have absorption. So it's proportional to both the amount of emission present, amount of photons present at frequency nu naught, and the density of electrons in level 1. Okay. The other concept that we will need is something called a line profile. Okay, so what is a line profile? So when you have this emission and absorption happening, the frequency, the photons do not come out at a fixed frequency nu naught. There is always broadening. Okay, and because of this, if you don't have any other physics, even laws of quantum mechanics tell us that these levels are not very sharp. There is like uncertain, because of the uncertainty principle, there is fuzziness in these levels. So that fuzziness is actually quantified by something called the line profile, which is denoted by phi nu, right? So phi nu as a function of nu is the function line profile, and this is a sharply peaked function at frequency close to this resonance frequency nu naught. Right, so this is frequency nu naught. So the probability of absorption and emission of photons because of transition between these levels 1 and 2 is sharply peaked close to nu naught. Okay, so this is what line profile quantifies, and you know this is sort of like a kernel function. So phi nu d nu is equal to 1. So basically area under this curve is unity. Okay, so what Einstein said is that, so let me write, so this is B12, this is the second Einstein, so this is the first Einstein coefficient, B12 is the second Einstein coefficient. What he said is B12 times J bar, right? So first let me write down and then I'll explain what I mean by J bar. So B12 J bar is equal to transition probability per unit time for absorption. Okay, so so jumping from 1 to 2 by absorption of photons is described by this transition probability, which is proportional to this average mean intensity of the photons present. So let me define what J bar is. With J bar is equal to integral from 0 to infinity J nu phi nu d nu. Basically, J bar is the you know the mean intensity of background radiation which is present. Okay, so this is absorption. Now, so this emission and absorption processes are reasonably intuitive, but what Einstein realized was that with just spontaneous emission and absorption, one cannot get Planck distribution in equilibrium. So by closely looking at Planck distribution, he postulated that one must have another process which is called stimulated emission at the microscopic level that must that's necessary to get the Planck form for the black body radiation, Planck spectrum. Okay, so what is stimulated emission? So this is spontaneous emission, right? Spontaneous emission doesn't require any background light, any background radiation. Absorption requires background radiation, but there is also another kind of emission which depend on the presence of background radiation, and this is called stimulated emission. Okay, so let me write down what are the transitions, what is the transition probability due to stimulated emission. So this is that. So this is the third Einstein coefficient, Einstein A, B12 and B21. So B12 is the coefficient which quantifies the probability of jump from 1 to 2, and 21 is jump from 2 to 1 due to in presence of background radiation. Okay, so this is transition probability per unit time for stimulated emission. Okay. So again, when you have emission, it also is so just like absorption, emission is also characterized by this line profile phi nu, and we can actually assume that the line profile for absorption and stimulated emission are similar, and there is like fundamental reasons for that, but we'll not go into that. But you know, as we also saw in Kirchhoff's law, emission and absorption processes are very closely related. Okay, so again, J bar is the same thing that I have written here. Here in this expression for stimulated emission transition probability, J bar is this integrated mean intensity across the line profile. Okay, and you know, you can actually, this is it is a good approximation to approximate phi as a delta function centered at the transition frequency mu naught. Okay, so these are the three processes. These are actually very, very fundamental. Okay, so let me create a little more space.
Sir, I have a question.
Yes, yes, please go ahead.
Sir, sir, this line profile you were saying.
Asking question, Kenyan?
Amlan, sir.
Amlan. Okay, yeah, it's good if you speak, if you take your name so that I know. I can connect voice to person. Yes.
So this line profile you are saying, is it the absorption spectrum line profile? Or,
yes. Yes, these are related to the absorption or emission line profiles that are seen in spectra, right? Here, yes. Here I'm assuming natural broadening, but if you have gas in motion, you have other processes like Doppler broadening, turbulent broadening, and so on. Okay, so this takes care of all that.
But sir, the mean intensity you are calculating,
yes.
there the JNU is the intensity of the background photons that are coming. So then the
J is the intensity of photons that are present, that the atom is exposed to. Okay, it need not be coming from background. You know, it can be self-generated light. There is no need for a background photons. This is the ambient photons that are present in the medium. Okay, you can have background radiation, but you don't need that. So for example, if you consider a black body emitting, you don't need any background radiation. Just the fact that the temperature is non-zero, you will have spontaneous emission that produces some radiation that, you know, that is absorbed, and you know, so all these things happen at the same time. And you don't need any background light for it to happen. Okay.
Okay.
Good. Okay, so let's go. Yeah. Right. So, so these Einstein coefficients A and B, A1, A21, B12, and B21 are closely related. Okay. And how do we see that? So let's consider in thermodynamic equilibrium. Right. In thermodynamic equilibrium, these two levels that we considered, level 1 and 2, right? The electron, you know, the electron density in level 1 and level 2, or atoms with electrons in level 1 and level 2, the population should not change in equilibrium. So what I can actually say is the rate of jump from 2 to 1, right? The rate at which atoms in state 2 jump to state 1 is the same as the rate at which atoms in state 1 are excited to state 2. Okay, or mathematically, I can write N2A21 plus N2B21 J bar is equal to N1B12 J bar, right? What I have, so this, so there are two processes which brings electrons down. One is spontaneous emission, emission, and the other is stimulated emission, right? And these are the expression for the two. So this B21 J bar was transition probability per unit time, but you multiply it by the density of atoms in that particular state, so you get probability per unit time per unit volume. Okay, so this is probability density per unit time for downward transitions. In equilibrium, it has to be equal to the upward transition probability rate absorption due to absorption.
I have a
Yes.
question, sir. The fact that
First tell your name,
you
please.
are describing. So I'm Sachin.
Yes, Sachin.
So the fact that you are saying that the electron is jumping from level 1 to level 2, and you are describing as N2A21 means some are equal. This may I'm thinking this like this due to thermal agitation these jumps are taking place. You are not considering any radiation right now.
No, this J bar is radiation field, right?
So the thermal radiation now due to
some radiation. I mean, when I'm doing thermodynamic equilibrium, yes, it will become thermalized. Okay, when you are considering thermodynamic equilibrium, so here I'm actually assuming thermodynamic equilibrium. I'm not assuming radiation and matter to be in equilibrium. What I'm assuming is that level population, that is matter. So I'm assuming basically LTE, but I'm not assuming J bar to be black body. Okay. But I'm considering these levels, the electron levels are consistent with Boltzmann distribution. Okay. So all I'm saying is that if the level populations are equilibrium, the rate at which the upward transition and the downward transition happen at the same rate. This is this equation. Okay. Is this clear?
Yes, sir.
Okay, good. So J bar is equal to, I just sort of rearrange it. I get A21 divided by B21 divided by N1 by N2, B12 by B21 minus 1. Okay, I'm just sort of rearranging this equation and I'm writing J bar in terms of everything else. And this is a nice form to write it in. Okay, and if matter is in thermodynamic equilibrium, the level populations are distributed according to Boltzmann, right? So N1 by N2 is equal to G1 by G2 e to the power minus delta E. This delta E is the energy difference between level 1 and 2 divided by KT, right? This is just Boltzmann factor. Level populations. Now this G1, so N1 is the number density of atoms in state 1, N2 is the number density of atoms in state 2. These are degeneracy factors of state 1 and state 2. So this is degeneracy factors, right? For example, in hydrogen atom, we know that the degeneracy of level N is 2n squared, right? So these are degeneracy factors of these levels. Now, right. So basically we can actually simplify this. and delta E, of course, is delta E is equal to H nu naught, right? That's the energy difference between the two states. Okay, so J bar can actually be written as A21 divided by B21 and by B12 divided by B21 times G1 by G2. I'm just writing N1 by N2 from there, times e to the h nu naught by kt minus 1. Does this look somewhat familiar to the black body Planck function? You see this factor at the bottom? This looks very similar to the Planck form that we had, right? And if you sort of trace back the origin of this term, it really is because of this one, right? The stimulated emission term gave rise to this minus 1 here, right? Because we divided by N2 B21 the whole equation, and this became 1 times J bar. Okay, so this is due to stimulated emission. Okay, so to get the Planck form right, you have to include this process. If you only had emission and absorption, you won't get this term right. You won't get the Planck form. And this is what sort of led Einstein to sort of introduce this microscopic process of stimulated emission. Okay, because you have like a Planck universal law for intensity, but you would like to have an even better microscopic description. Okay, so that's why he introduced spontaneous emission. Okay, and we know the black body function B nu T, right, is equal to 2 times. So this is the degeneracy factor, H nu cube by C squared 1 by e to the H nu by kt minus 1, right? So this is the specific intensity that we get when matter and radiation are in perfect equilibrium, right, which is the black body function. So if we assume equilibrium between matter and radiation, then we can actually read off, right? We can actually compare these two expressions and obtain relations between these A and B coefficients. So we can actually just see that this factor B12 G1 should be equal to B21 G2. So B12 G1 should be equal to B21 G2. Right, so A, B relations. So these are the relations between Einstein A and B. Because if you have enough interaction between matter and radiation, this should be the same as B, right? The specific mean intensity should approach the Planck function. Okay, what about this? We can also compare A21 by B21 to this twice H nu cube by C squared. So we have A21 is equal to twice H nu cube by C squared B21. So you only need to know one Einstein coefficient. So if you know A21, you know everything else because they are proportional to each other. So this also sort of means that a good emitter, right? A good emitter, which is it's a material which has a high A21, is also a good absorber because B12 is proportional to B21 and is proportional to A21. So this is sort of like a microscopic version of Kirchhoff's law, which was macroscopic and more in terms of material properties, but this is in terms of atomic physics processes. Okay, and you actually see that, so these are independent of temperature. Right? So there is no temperature appearing in these relations. So that means these apply at all temperatures, and that although we have motivated this from this equilibrium argument, these have to be universal. These relations between A's and B's apply even for non-equilibrium. So even when these levels 1 and 2 are not distributed according to Boltzmann, this relation has to hold, because these are like atomic physics processes. That if you go from 2 to 1, this is the rate. 1 to 2, these are the rates. And this type of arguments, where you are balancing microscopic processes between two states, is called detailed balance. So this is a detailed balance argument. Detailed balance. And this detailed balance applies even when you don't have equilibrium. In fact, the way to derive this relations between A and B, assuming thermodynamic equilibrium, may seem to suggest that this is this only applies for thermal equilibrium situation, but this is not true. These are actually detailed balance arguments that, if you have levels 1 and 2, the rates taking you from 1 to 2 and from 2 to 1 are balanced by each other, right? So rate, going from here to here and there to here are balanced, and this is detailed balance. Okay, and in this case, and this applies to a lot of different microscopic processes in chemical kinetics, in ionization, recombination, and so on. So wherever you have microscopic sort of transitions, so whenever, or in other words, whenever you have like a reversible reaction, you can also, the rates of forward reaction and the backward reaction are related very, very closely through detailed balance arguments. Okay. The other thing about stimulated emission is that stimulated emission produces photons which are coherent, which are moving in the same direction, have the same frequency and same phases. Right, so stimulated emission is really the process which gives rise to the phenomenon of lasers. Okay, because the radiation gets amplified because of the presence of photons of the same frequency. Okay. So let me just write coherent directional photons. Okay, so now it actually produces photons which are in the same phase. Basically, they are the same state, quantum mechanical state of photons which are produced. Okay, so I think this page is full now. I'll actually go to the next page, which is this one. Okay, so now we'll actually try to express absorption and emission coefficients J nu and alpha nu in terms of Einstein A and B. So J nu and alpha nu in terms of Einstein A and B. Okay, how do we do that? It's actually fairly simple. You recall the energy emitted in a volume dV due to photons going in direction d omega in time dt and d nu is given by, right, so J nu times dV d omega dt d nu, right? So this is the energy dE due to photons, and we actually just wrote down this transition probability. So let me actually just write down the expression, and then I'll justify. This is the line profile, N2 A21. Actually, let me just also draw this level 1 and 2 times volume dV d omega d nu dt. So if you recall, A21 was the probability per unit time for the decay, right? So A21 times dt is a probability. A21 times dt is a probability for transition of electrons from level 2 to 1. And now if you multiply by N2, which is the number density, so number per unit volume of level 2, right? So this N2 times A21 times dt is number density of photons. Number density of photons. So times dV becomes number of photons produced in time dt. D omega by 4 pi is just solid angle normalization. You assume that they are isotropically emitted, so you just get d omega by 4 pi. And then you have h nu, that's the energy of the photons, and phi nu d nu is sort of like, it tells you how the frequency, how the photons are distributed. They are not exactly at nu naught, remember. There is a finite width to the line, so phi nu sort of quantifies this. So we can actually just compare these two, and we can actually just cancel these. dV goes out, d omega d nu dt. So basically what it tells us is that J nu, right? So this just gives us J nu in terms of Einstein A and N2. Okay. What about absorption? So this is emission. So we have related emission, the microscopic and macroscopic emission, spontaneous emission. Actually, you should spontaneous, because we have other kind of emission, which is stimulated emission, but it's it is much closer to absorption than to stimulated emission. Reason being, it also requires background radiation to be present. Okay, let's look at this. So so the macroscopic, so the energy absorbed, right, is equal to alpha nu I nu d nu dA d omega ds. If you recall, this is how much energy is absorbed. So ds is the path length along the ray, d omega is the solid angle, dA is the area of the beam, d nu is the frequency width. So this is the macroscopic expression for absorption, energy absorbed, right? So let's try to see, let's try to write the microscopic expression. Okay, let me see. So we have N1. So let's just consider only absorption for now. Only absorption, no stimulated emission for now. So this will be just N1 times B12 times dt, right? So N1 times B12, sorry, there is also J nu, so J nu, right? So this portion is just the probability per unit time. So if you multiply by dt, it's just probability of transition from 1 to 2. Okay, so this is the probability. Okay, and then let me put other factors, the d nu, the so phi nu d nu h nu, right? This is the energy, d omega by 4 pi, the solid angle factor. Right, I think everything is taken care of. N1. So now this is this is per unit volume times the volume. So this becomes just a number. So this is number of transitions from 1 to 2. And in each of these transitions, you have energy h nu absorbed. So this is, this is what you compare. So you actually realize that dA times ds is nothing but dV. We did this in radiative transfer. And we get this expression for alpha nu when we cancel out all these factors. We get alpha nu is equal to h nu by 4 pi times n1 b12 times phi nu. Okay, now if we include, so with stimulated emission, as I said, stimulated emission is almost like opposite of absorption, right? This is exactly opposite of absorption because the expressions are almost the same, except instead of absorption it's emission. So n2, so you will have n2 times b21, right? And everything else remains. So alpha nu, when you include stimulated emission in it, is given by h nu by 4 pi times n1 b12 minus n2 b21 times phi nu. Yeah, so all I have done is just included this n2 b21 with a negative sign, right? So notice this negative, this is because it's emission. And it has this form because this emission, like absorption, is also proportional to J, right? The radiation intensity present. Okay. So we can actually write the radiative transfer equation. So radiative transfer equation in terms of A and B, Einstein A and B. How do we do that? This is di nu by ds equals minus alpha nu I nu, right? So so that's what I have to write. So minus h nu by 4 pi phi nu n1 b12 minus n2 b21 times I nu plus, right, di nu by ds is, this is plus j nu, and j nu is nothing but h nu by 4 pi and 2a21 phi nu, right? So this is the radiative transfer equation. Instead of writing in terms of alpha nu and j nu, we are writing in terms of Einstein's A and B. Okay, and if you recall, we have the source function, source function S nu, and this S nu is nothing but J nu by alpha nu. This is equal to, right, if we just take the ratio of this and this, what do we get? We get N2A21 divided by N1B12 minus N2B21. This is the source function, and right, this is actually valid even if you have non-thermal emission, even if your matter is not in equilibrium. So valid in general. Because these A and B are valid in general, these are derived from detailed balance. Right? It doesn't depend only on the assumption of any sort of equilibrium. Okay. We can actually write it in terms of, by using Einstein, the relation between Einstein's A and B, we can actually write it as twice h nu cube by c squared. So right, this was the ratio right, this was the relationship between A and B. G2 n1 by G1 n2 minus. Right, if you recall, A21, right, so B12 and B21 were related. So let me see. I don't want to go back to the previous page because it sometimes it does not show up, or maybe should I try? Yes, this is what I was afraid of. Oh yeah, it did come right. So yeah, here it is. Right, so these are the relations that I'm using, right, and these are motivated from comparing with the Planck function. B12 G1 equals B21 G2, and A21 equals this times B21. These are fundamental. These do not depend on the assumption of equilibrium, although they are motivated from that assumption. Okay. Right, so that's how we actually take this ratio of, yeah, any question?
Sir?
Yes. First tell your name, please.
This Vishnu, have a question.
Yes.
So, stimulated emission is not isotropic, right?
That's correct.
Radiation from stimulated emission is not isotropic, right?
That's correct.
So in that case, the factor of 4 pi that we have included, t omega by 4 pi, should not be there for the other term, right? B21 term.
Right. So what we are assuming here is that we have these so you may have like some volume. We are assuming that all these things are oriented randomly. So this is actually a as an assumption, but what you're saying is absolutely right, that stimulated emission is directed, and you should not do this 1 by 4 pi. Here inherently I have assumed that, but again this is sort of related to the question that you asked in our you asked that alpha nu should depend on the direction in which you are considering the ray to be propagating, and that's actually right. In the same way, you can actually incorporate this effect in these radiative transfer equations. You can actually consider photons going along a certain direction, and you can actually have, so if you have anisotropy in the radiation, for example, if you have photons going preferentially in this direction, and if stimulated emission dominates, this can actually this can be the direction of photons. All the other photons are very small in number compared to these, and this actually can be incorporated, but I'm not doing the general case here. Okay.
Yeah. Okay.
Right. So yeah, you're right that this is not the general case. Okay. So we were here. Right. So this expression, this is actually valid in general, right? But when you have matter in equilibrium, this is just given by, right? So this is given by e to the minus h nu by kt when LTE, when matter is in local thermodynamic equilibrium. But this is not true in general. Sorry, plus because we have N1 in the denominator. Okay. So for LTE, what do we have? We have G2 N1 by G1 N2 equals e to the minus h nu by kt. And what happens in that case? S nu is equal to B nu T, right? Because this just becomes Planck formula, right? For LTE, this is what happens. That you get the Planck formula and your source function becomes B nu, the black body function or the Planck function. And what happens to the alpha nu? Alpha nu is equal to h nu by 4 pi n1 b12 times 1 minus e to the minus h nu by kt times phi nu, the line profile. So you actually, let's go up a little bit. So this was alpha nu, right? This is a general expression. So we bring out n1 b12, this becomes 1 minus n2 b21 divided by n1 b12 using the relations between Einstein, these Einstein's coefficients. We actually can write this in terms of n1 and n2, right, in general. So this, this thing, this should actually in general be replaced by n2 g1 by n1 g2 in general. But when matter is in LTE, this becomes this. So you see, alpha nu is always greater than 0 for thermal emission, right? Because this expression 1 minus e to the minus h nu by kt is always positive. So alpha nu is always greater than 0. You can only have absorption, net absorption, in case of thermal processes where the level populations are in LTE. Okay, and you realize that this is due to stimulated emission. So in the Rayleigh-Jeans regime, right, in the Rayleigh-Jeans regime, which is the low frequency regime, right, this e to the minus h nu by kt factor almost balances this absorption. So stimulated emission is extremely important in the Rayleigh-Jeans limit, in the low frequency limit, because absorption is almost exactly cancelled by stimulated emission, right? In such a situation, when h nu by kt is small, the two populations, the level 2, level 1, so level 2 also has significant population. So you should consider this stimulated emission when you're sort of taking care of absorption. So, right, so this is in the Rayleigh-Jeans limit. Now in the other limit, in the Wien limit, right, in the Wien limit, what you know is that basically h nu is much greater than kt. In this case, what happens is this is negligible, right? N2 is very, very small compared to N1 because of this exponential suppression. So, right, e to the minus h nu by kt in that case is much less than 1. Right, and the photon discreteness effects become important. That is, photons have E equals h nu. If you go to very high frequencies, you won't have, there is an exponential suppression of photons with that energy. So this is the Wien limit. In this case, you can ignore, basically this is equivalent to ignoring stimulated emission. So Wayne approximation is equivalent of ignoring stimulated emission, and that's justified in that limit because N2 is much smaller than N1. E to the minus h nu by kT is much smaller than 1. So this is for LTE. Now for non-thermal emission. So if the level populations are not according to LTE, so N1 by N2 is not equal to G1 by G2 e to the h nu by kT, right? This is the case. You know, this will apply, for example, if you have non-Maxwellian plasma, you know, non-Maxwellian, so when you have a plasma whose energy distribution is not Maxwell-Boltzmann plasma, or for example, if you have scattering, you know, if you have an atmosphere which is dominated by scattering, in that case too, the level populations are not given by this, right? In case of scattering, photon number is conserved, photon number conserved, right? So when the photon number is conserved, you cannot have a Planck distribution, because Planck distribution assumes that the photons can be created and destroyed on demand and sort of approach the Planck distribution. So for scattering dominated atmosphere, the mu chemical potential is not equal to 0, right? So this is not given by e to the h nu by kT. There is also a h nu plus mu by kT. Okay, so this is for scattering. So in these general situations, N1 by N2 is not given by this, and so you have two cases in the two scenarios in this case. In the non-thermal case, what are the two scenarios? The first is when you have normal population of the levels, and the second is in population inversion.
Sir?
Yes.
This is Vishnu. Can you elaborate on the point in which you said mu is not equal to 0 in case of scattering?
Right. So in scattering processes, right, you don't have emission, you don't have absorption. All you have is you have a photon which is going in this direction, interacts with an electron, and after collision it moves in some other direction, right? The photons cannot be created or destroyed in scattering. So even if you have a lot of scattering in an atmosphere, it will not approach black body distribution. Okay, and scattering is very, very important, like, you know, Thomson scattering, Thomson scattering, and Compton scattering. These are the processes. Even if you have a high probability of scattering, such an atmosphere will not will not emit a black body radiation. What it will emit is something like a modified black body, which has e to the h nu minus mu by kT minus 1. So, you know, it has a Bose-Einstein. This is average occupation for a Bose-Einstein boson gas, right? So this mu is 0 for photons. That's why that's the Planck distribution. But mu is not equal to 0 in absence of absorption and emission, in absence of absorption and emission. And if you only have scattering, this is what happens. Okay, so this is a little more on this. Okay. Normal populations. Is this fine? You know, I don't want to get too much into this. We'll actually come to scattering later. But scattering is very different from true absorption. Okay, so just having a lot of scattering will not relax your I nu to B nu. It will relax it to something which has a non-zero mu. So it's not a Planck function anymore, even if you have a lot of scatterings.
Yeah, all right.
Okay, so normal population means that N1 by G1 is greater than N2 by G2, right? If you have this, then let's see what happens, right? So this, right? So N2 G1 divided by N1 G2, in this case, alpha nu, right? In the normal populations, alpha nu is greater than 0, right? You can actually look. This was only true for thermal level populations, but in general, it's that. If you have normal populations, N2 G1 divided by N1 G2 is less than 1. So alpha nu is greater than 0. But population inversion happens when it's the other way around. When the excited level is populated higher than the equilibrium distribution. Okay, in this case, alpha nu can be negative. So you have negative absorption, which is, this is basically a stimulated emission. So, for example, in such a medium, so if you have a medium with such a condition, so and if it is optically thin, if you have some radiation coming from the back, if you measure it here, I is equal to I naught e to the minus alpha nu times the length, right? This is just optical depth. Alpha nu ds integral is just tau nu. Right? So you have absorption of radiation, and the outcoming radiation has lower energy, has lower intensity compared to the incoming radiation. Now, but if you have negative absorption, what happens is I in the same situation is I naught times e to the alpha nu times L, right? The outcoming intensity is much higher and exponentially higher than the ingoing one. So, or tau nu is negative, right? So you have emission. So even a small column can give you a huge intensity coming if you have population inversion. And in fact, in nature, you do see this this phenomenon is called maser, right? So microwave amplification of radiation. I actually forget the laser. What does laser stand for? Light
Amplification by process of stimulated emission of radiation.
Yes. So microwave amplification of radiation due to stimulated emission. This happens. So this was mostly observed in microwave range, wave range. So centimeter wavelength. So that's why this was called maser. In fact, masers were discovered first before lasers and in astronomy. Okay, and actually what you see is some of these molecular lines, molecular transitions, like in water. You can get water masers which are very, very bright because of this exponential enhancement of background radiation at certain frequencies. Okay, so for example, if you have tau of minus 100, right? If you have optical depth of 100 but negative value, you can actually get a amplification of the background radiation by a factor of 10 to the 43. Right? So this is e to the 100. E to the 100 is 10 to the 43. So this is, this actually happens, right? But it can only happen in non-equilibrium conditions. For example, in a lot of cases where you have fluorescence, what happens is, you have three sort of levels. So what happens is there is background radiation which excites this electrons in this level to this level, and they very quickly decay to this metastable state. Okay, so this level is, this is having population inversion. So you have, this stimulated emission is much more common than absorption, and you have alpha nu less than 0. So this is what happens in lasers too, except in lasers we control it, but even without controlling it in astrophysics, since the densities and so on are not very high, and some of these transitions are not that fast, you can have levels which are populated more than their equilibrium level populations. So for example, these water masers and so on. Okay, so this is actually an important phenomenon that actually also happens naturally. Of course, technology, laser is ubiquitous nowadays, and we use it in all processes. But the processes, the physics principle of laser is very, very similar to what I just described, and it can all be traced back to the stimulated emission which Einstein introduced. Right? If you don't have this term, there is no way this alpha nu can be negative. So in case of lasers, what we do is we actually create these resonant cavity, and we let the radiation sort of jump back and forth, and we can actually get huge amplification over small lengths. But in nature, in astrophysics, you don't have such a cavity, but you have very long path lengths. And if you have very long path lengths, of order, say, parsecs, then you can actually get a very high amplification factor just naturally, right? Except in lab we control it much more, and we let the photon beam sort of traverse a long distance by reflecting it partially. Okay, so this is actually, this is the principle behind lasers at a fundamental level. Okay, so this is this. Okay, so let me actually also, I wanted to mention briefly about scattering. So we will actually not be doing scattering, radiation transfer with scattering in this course, but I will actually briefly mention the process of scattering. Okay, so let me actually create a new page. So let me just write, and I'll just sort of briefly and very phenomenologically explain scattering. Oops, what happened? Oops. Why am I not able to write? Okay. This is fine. Okay, good. I think there's a lag when I sort of start anything new. There is a lag. So scattering. So let me also put today's date. So 21 October part 3. Okay, scattering. Right. So so we already talked about processes of emission and absorption. Scattering is a distinct process. Okay. In scattering, photon cannot be eaten up by atoms. It can only change direction. So you have a photon and you have some free electron or an atom or whatever. So after this collision, what happens is the photon direction changes, right? But the number of photons remains conserved. Whatever came in has to go out. So it conserves number. But when the photon number is conserved, you cannot achieve black body function. You need absorption and emission for that. Okay, so what happens with scattering is, I actually briefly mentioned it. If you consider a beam of photons traveling in this solid in this direction, so you will have some of these photons, moving out of the beam, and some of the other photons which are traveling in some other direction getting scattered into the beam. Okay, so in this case, your S nu, which was equal to B nu in presence of just absorption, becomes more complicated. It becomes a non-local function. S nu in presence of pure scattering is just I nu d omega by 4 pi. Basically, what I'm saying here is that if you have many scatterings of your photons by electrons, what will happen is the mean intensity in a particular direction, right, reaches an isotropic value of the intensity. This is just isotropic value of the intensity, or which is nothing but J nu, right? This is the definition of mean intensity. So it is not like a universal function in this case, right? So you have to actually solve for I nu in all these different directions, right? And once you have the solution, then if you average all those solutions over all solid angles, right, that is what your specific intensity is. So it's like it's an integral differential equation for the radiative transfer with scattering. So we'll actually not do it. In fact, this is important, but we will actually not do it because this is somewhat technical, but it's important to know this phenomenon. Okay, now let me actually also tell you this famous random walk picture of scattering. So you can think of scattering in terms of a random walk. So if you have a photon which starts from here, goes to this point in a straight line, here again in a straight line, somewhere back there, so this is the picture of scattering or random walk, right? So basically, suppose you consider so this is suppose you consider the origin, right, of your coordinate systems here, and you consider R is equal to, so this is your R, this is like your final position of the photon after certain number of scattering. So this is R, right? What is R? R is nothing but R1, the first step in scattering, plus R2 plus dot plus Rn. Okay, so these are the tiny steps that the photon takes during scattering, and at the end of n scatterings, this reaches a distance capital R, which is given here, shown here in this red arrow. Now, if you take an ensemble average of R, if you have a lot of realizations of these n scatterings, in some scattering this final position will be here, this will just be ensemble average of all these individual steps, right? And we know that in general, if scattering is isotropic, the photon has equal probability of going in any direction and in any other opposite direction. So these are all zero, right? So the expectation value of position after n scatterings is actually zero. Does this mean that the photon does not move at all from its original position? No, that's not true, right? We should actually talk about the expectation value of R square, the final position squared. So that is nothing but R1 plus R2 plus these individual steps dot R1 plus R2 plus dot, right? So this expectation value. Now, what is it? It's R1 squared expectation value, and all these steps are independent steps. So they are statistics. So the length in each scattering is statistically the same in each scattering. So this Ri square just gives you n times R1 squared, because they are all equivalent, so they are just add up, and you have contributions like Ri, Rj, Ri dot Rj. So you will have contributions like this, where I is not equal to j. You have these pairs of r's appearing, and we say that each scattering is independent. So so the directions of ith scattering and jth scattering are totally uncorrelated. So this is 0. So basically what it tells us is that r squared is given by n times L, right? If L is this individual L, or mean free path of photons, if L is the mean free path of the photons, this average scattering length in each step, then the RMS distance squared is approximately number of scatterings times the length covered in each scattering, or the mean free path. Okay, so, and we can actually also sort of define tau. The optical depth is nothing but the system size divided by the mean free path, right? This is actually, if you recall, the mean free path was nothing but 1 by alpha. When we are doing radiative transfer, mean free path, or lambda mean free path, is 1 by alpha. So this is just alpha times L, which is the optical depth. Now the number of scatterings, so number of scatterings is equal to, so if you have like an object of size L, right? And if you consider photon starting from here, how many times will it scatter in such a medium, right? For example, if you consider photon starting at the center of the sun, how many times does it sort of scatter, or does it undergo absorption as it emerges out, right? So this is nothing but sorry, this is L squared, right? Because this R squared is nothing but L squared. Ri squared is nothing but L squared. So number of scattering is just L by L squared. This is for L is much less than L, right? When you have many scatterings, so this is or for optically thick conditions, right? But in optically thin condition, what happens is it's only in a single. So if you have an optically thin condition, only in a single step it will just come out with a probability, right? With a probability L by L. The probability of coming out is just this, when tau is much less than 1. So in this case, n, an average value of n will just be L by L, right? This is the ballistic limit, when you don't have any scattering, and this is the scattering limit, scattering optically thick limit, right? So we can actually say that number of scatterings is equal to, is roughly given by max of tau and tau squared, right? Tau is the optical depth. So remember, tau is equal to L by small l, right? The ratio of the global size of the system and the mean free path. Now when tau is much less than 1, right, n scattering is nothing but tau, right? Because epsilon square is smaller than epsilon, right? So so n scattering is just tau in that limit. When tau is much bigger than 1, right, then you have many scatterings, and you are in this regime, which is nothing but tau square. So these, this is sort of the very crude picture of scattering that I just want you to be familiar with. In fact, what I should do is,
sir, this is Kinjal.
Yes, Kinjal.
Sorry. Can you just restate the one where the optically thin? Can you just explain it once again?
Yes, that's correct. So this is an optically thin case. So if it has a size L, right, and if I populate many photons here, right, what is the fraction of photons which will be absorbed? It will just be small l by capital L, right? Because this has a capital L by small l, right? Sorry. So L is much less than small l. So the mean free path is big compared to the system size. So what is the probability of absorption? Probability of absorption is actually, sorry, the other way around. Thanks. Probability of absorption is just L by L. So this is the probability of absorption, and this is the number, right? Number is just inverse of probability in this case, when probability is less than 1. Right? So this is actually just the fact that, you know, e to the minus tau nu, right? This is e to the minus tau nu. So this is what? This is transmission fraction, right? Transmitted fraction is just e to the minus tau nu. When tau nu is much less than 1, right? This is nothing but 1 minus tau nu. So the reflection fraction or the scattered fraction is just
Thank you.
right. So this is just like this is just like a radioactive decay type of an argument, right? If you're waiting for less than a half life, then right, so then the probability of decay is just given by the ratio of dt by t half, right? It's that limit. Here, you know, you're in the opposite limit. Yeah, sorry. This is actually given in Rybicki Enlightenment, you can read up. But I think we are done with the first module of this course, which is chapter 1 in Rybicki Enlightenment. As I said, I've not really done scattering in great detail. I've just sort of sketched it out qualitatively, but I think that's good enough for this course. If anyone sort of needs it in their research, they can always pick it up. So the last 2 sections in Rybicki Enlightenment are devoted, in the first chapter, are devoted to scattering. Okay, and you guys can, you know, read up there. And in general, Rybicki Enlightenment is a standard reference on concepts of radiative processes. Okay, so now after this, we will actually start with chapter 2, and we'll go to classical radiation theory, like retarded potentials and so on. We'll not do great physics behind those, but we'll use results from advanced electromagnetism. Okay. So I'll actually stop sharing, or are there any questions?
So sir, I mean, there are a few topics after this. So do we need to study them, like plane parallel atmosphere and all those things?
You don't have to study them for the exam, no. But you know, if
Okay.
you have time and if you're enthusiastic, you should read it. It's all, you know, it's very educational stuff, but not for the course and the exams. Okay, because you know, if you look at the syllabus of the course, for example, right, I will actually try to follow the syllabus closely. And if you look at that, you know, definitions of specific intensity, mean intensity, flux, energy density, equation of radiative transfer, solutions in specific cases, optical depth, thermal emission, black body spectrum, its characteristics, Kirchhoff's law, Einstein's coefficient, right? There is no scattering here. Okay, so I will actually try to closely follow this. Okay, but you know, scattering is very, very important. And in fact, we'll encounter it later. You can actually see Thomson scattering here and Compton scattering here. But we will not do radiative transfer with scattering. This radiative transfer is over. I mean, it's a huge subject. There are books on this, but we have only scratched the surface. But that is the purpose of this course, that you know, we don't get into details of any of these very deeply, but we should be at a level where anyone who needs it for research can, you know, dive from this starting point. Okay, any other question? If not, I will actually end this session. So Monday is a holiday, I believe. It's Dashera, next Monday, 26th.
Yes, sir. I think
So we will actually, it will be off then, we'll take a holiday. And the good thing is we are also done with this module. So I can also take a break of a day. Okay. So Monday there will be no class. 26th is a holiday. We'll meet again on Wednesday, which is 28th. Okay.
Okay, sir.
Bye then. I encourage you to look at the question. So the exam, right? So now we'll have the exam. So we will have exam based on this material and homework 1. I may actually add a little more, some more questions in homework 1. I will actually let you know on the channel if I do that. But what I was thinking was we can have exam either end of next week or the beginning of November. Okay, I will keep you posted. This will be the first of the 4 exams. Okay. Bye. I'll keep you posted on the channel.
sir, recording.
Yes, I have to stop recording. But do keep reading and do keep looking at